Thanks very much, Chris, Ben, Dean. It's always an honor to be the first speaker in a conference like this, but it's especially an honor to be the first speaker on the first ever conference on aerial robotics and drones. It's a real pleasure to be here, and I'm really thankful for this opportunity to share with you some of the work that my students and I are doing on unmanned aerial vehicles. As you know, the industry is experiencing exponential growth. If you look at this curve, this chart, it looks pretty ordinary, but just pay attention to the y-axis, which is logarithmic. For all us nerds out there, that makes sense. The number of UAVs worldwide is increasing dramatically. It's a $10 billion industry. In the US alone, there's about 7,500 UAVs. There's over 75 countries that are investing in UAV technology. But the excitement really comes from all the civilian applications that we're going to be talking about at this conference, and particularly all the do-it-yourselfers that are out there, millions of them all around the world. There are startups, exciting startups being formed in this space every day. Matternet, interested in logistics and transportation. HaloDrop, coordinating FEMA operations with small UAVs. 3D robotics, of course, with Chris Anderson. Skycatch, interested in monitoring construction sites and precision farming, aerial photography. A company that we've been working with, a spin-off from our lab, Identified Technologies, where they're using robots with ground-penetrating radar to detect IEDs to enable convoys to progress more quickly through fields that might have IEDs buried. KML Robotics, and this application we're looking at has to do with inspection, the insides of penstocks of hydroelectric dams. And you can see this image here taken from a small quadrotor, which essentially shows a corroded spot in this penstock. So there are lots of UAVs that we read about in the press. Most of them have to do with military UAVs. These are the big, large UAVs on the right side. And of course, these UAVs, we have to remember, are controlled by flight crew, and this is just two people in New Mexico Air Base that are driving it. One of them is actually joysticking this UAV. The other one is looking at the sensors. Sensors feed from the UAVs. But you have to remember there's a flight crew, oftentimes 10 to 20 people behind each of these UAVs, and they're really remotely piloted aircrafts, as General Norton Schwartz said. And in fact, he objects to the use of the word drones, as I do. What we want to do really is build UAVs that are autonomous, which are not really drones, aircrafts that can think for themselves and do the right thing. Our interests are not in these big UAVs. We build UAVs that are really small, at most a meter in diameter, and capable of navigating rooms like this in hallways. The smallest one, we now 3D print these, and it takes about 2 hours to print one of these. And it's smaller than the size of my palm. And I'll show you some of these videos as we go through the presentation. The best design, if you want to build lots and lots of these, and we're interested in building swarms of these, is the quadrotor. There's nothing simpler than that, a rigid structure with motors and 4 propellers, and a microcontroller that controls the speeds. But of course, you all know this. One thing I would emphasize is that size does matter. If you make things smaller, if you shrink the size, and if you take this length r and you look at the physics of what happens when you take r and reduce it to r divided by 2, you'll find that the mass decreases substantially, the inertia decreases substantially, even the thrust decreases. But the key point is that if you look at the acceleration of the UAV, it actually increases. So if you take r and divide it by 2, the acceleration doubles. The angular acceleration actually quadruples. So you can make robots that move really quickly, as this really small prototype and that you can see in this video. On the top, you see the robot able to stabilize pretty quickly. Again, if you have very low inertia, you have a lot of control, and you're able to recover from all kinds of configurations. In the bottom, you see the UAV essentially performing these double flips, and it can do it at fractions of a second, reaching speeds of about 2,000 degrees per second. So we're interested in making these small UAVs, particularly for search and rescue. So this is a picture taken from an experiment we did shortly after the earthquake in Japan, in Sendai, and I'll talk more about this going forward. Obviously, security applications are big. So here you see a UAV performing autonomous patrolling operations in a warehouse-type complex. And with a simple camera, you can actually detect features on the ground. You can track cars. You can track people. So if you see that white Ford Bronco, you can tail it. So these kinds of things are actually very, very feasible. And this is something we're doing with KML Robotics. We're really interested in operations and first response. So in first response, the challenge is you have to enter buildings like this from the outside. So you have to operate indoors and outdoors. There is no GPS indoors. And you want these robots to be really small and maneuverable in tight spaces, go through windows, doors, and you want them to be really fast. Usually first response operations have to be done in seconds or at most minutes. And so you want these robots to respond really quickly to human commands. Lastly, we want these robots to operate in teams. If you have small robots, chances are that individual robots may not be able to perform all the tasks that you need. So you really want a lot of these to collaborate to perform the tasks. So these are the things we're trying to look at in our lab. So I want to give you a hint of some of the technology challenges that we work on, maybe spend 5 minutes in each area. So the first thing that I want to talk about is how we think about the dynamics of these little vehicles and how we try to model them, how we get them to go really quickly through complex environments. So here's just a rough schematic of the control loops that we try to build. You'll see 3 sets of feedback loops. The innermost loop feeds back the orientation of the robot and the angular velocity at about 1,000 times a second, so of the order of 1,000 hertz. And it's vital to get this right, because what you really want to do is for the robot to be able to recover from whatever configuration it's in. So this is the attitude controller that is on board in this picture. The intermediate loop closes the loop around the position variable. So you sense where you are in the environment, how quickly you're traveling, what's your velocity, and the position controller tries to follow the trajectory that's then specified by the outermost loop, which is the planner, which basically says if I want to get from here to there, if there are obstacles in the environment, what's the best trajectory to follow? And that's being done at the outermost level, and that's being done 10 times a second. So you have control loops at 100 hertz, 1,000 hertz, 100 hertz, and then 10 hertz. And in this particular picture, you'll see that we actually use some of the computation from laptops that are off-board, and the sensing is obtained by motion capture cameras that are sensing position and velocity 100 times a second. This may not all be feasible but in the outside world, but this is where we do our development. This is where we finesse, we develop algorithms, we test them, we evaluate them, and so on. I want to show you a couple of video clips that illustrate the agility of our robots. The first one is basically showing how our robot goes from point A to point B through an intermediate point C. And you'll see the really large roll and pitch angles that the robot has to automatically figure out how to execute this. And it pitches forward and then it rolls to the side to make this tight turn in a fairly small room. And we call these trajectories minimum snap trajectories because these robots are actually trying to optimize a dynamic variable, which is called snap, which has to do with the fourth derivative of position. So once you know how to do that, you can also go through obstacles. So here these obstacles are represented as hoops. The robot knows where the hoops are, and it's basically trying to figure out what minimum snap trajectory will carry it through these hoops. And again, everything in this environment is completely known. The motion capture cameras on top are telling the robot where everything is with split-second timing. And here you see the hoop being thrown into the air. Well, the robot knows the hoop is in the air, and it figures out how to go through the hoop. And again, if you have these loops carefully tuned, carefully designed, then you can actually do these split-second precision maneuvers quite efficiently. So this is key to get the robots to perform in an agile fashion in three-dimensional environments. I want to go to the next challenge, which is I showed you all these cameras. How do I get rid of these cameras and make these robots truly autonomous? In other words, how do I get the robot to determine what its state is, estimate its state? State meaning position, velocity, orientation, and so on. So again, in this picture, what I want to do is get rid of the motion capture cameras and get rid of off-board computers. So the key idea here goes back at least 3 years. We took a slightly bigger quadrotor and put on it a Hokuyu laser scanner. So this laser scanner is able to send out beams over a 270-degree field of view, and it's able to map obstacles in the environment. And that is key in order for the robot to figure out where it is. In order to explain this technical idea, let me show you a cartoon. So in this cartoon, you see this robot with 3 pillars. The robot does not know where it is, neither does it know where the 3 pillars are. But if it's equipped with this laser scanner, it can measure the range to these 3 pillars. So it can measure these variables D1, D2, D3. Now imagine a robot takes a small step. So it doesn't know how far it's moved, but it has some idea of how far it's moved from onboard sensors, the accelerometers and the gyros. So it has some measure of delta x. When it goes to this new position, it's able to again measure with its laser range finder, get these 3 additional pieces of information. These distances, D1, D2, D3, are different from the original distances. So it has some estimates of the 3 early measured distances, and now the 3 current measured distances, and it knows roughly what delta x is. So now the key question is, can you figure out where the pillars are and how far you've moved? Well, if you write down a few equations, and this is just geometry, trigonometry, you should be able to convince yourself that you can, in fact, solve for these 8 variables armed with the pieces of information that you measure from the sensors. Of course, life is a little more complicated because the measurements that you make are noisy, and to solve for the best estimates is oftentimes hard, and plus you have to do it in real time. But this is the key idea behind what is called simultaneous localization and mapping, where you're localizing yourself, measuring delta x, and you're also mapping where the pillars are. And in the robotics community, of course, we use this cool acronym SLAM. So when you see a problem like this, we slam it, right? But of course, we have to do it in real time. As you see in this vehicle that's taking off outside a building, what the robot sees is on the top right window, and the video on the bottom right tells you what the robot is actually doing. Its internal representation is on the left side. So on the left side, you will see it's measuring all the possible pillars, if you will, and it's actually mapping these pillars. And these pillars, quote unquote, are color-coded. You will see that the blue colors, the cool colors, represent the ground floor, and as the colors get hotter and hotter, you're going up to all the way to the 4th floor. So it's able to build a map as it moves, and the human operator is simply able to click on this interface on the left when he's outside the building and ask the robot where to go to in this map. And then the robot's able to plan an obstacle-free path. And in the process, the robot continues building up this map so that now you're getting the same kinds of 100 hertz update that you did earlier from the motion capture cameras, but now you're getting it from the lasers and the onboard computer. And of course, you can also use vision in the process, but this is the simplest algorithm that you can think of. So this was our first solution to the problem of how do I get rid of the motion capture cameras. Of course, the big problem is you build something like this, and I've been talking to you about building small vehicles, agile vehicles. You're going in the wrong direction. You want to put on a laser scanner, well, you just made it a little heavier, which means you needed to have bigger motors, bigger props. Well, that meant you needed bigger batteries, which in turn meant that you needed bigger motors again. So you're scaling in the wrong direction, and if you think about it, this vehicle consumes 400 watts of power. That's like 5 light bulbs, right? So this is a lot of power.